be some preliminaries. We got that. Okay. So there will be some preliminaries just where I explain some of the settings and stuff that you need for Protege and what's the objectives for this session. The key driving forces behind the research for description logics is expressiveness, computational complexity, and decidability. And I'll give you brief sort of intuitive definitions of these. Then I'll give some of the motivation behind why description logics is really important and why you would want to make use of description logics. And for that, we're going to look at prepositional logic, predicate logic, and then description logics. So the terminology between description logic and OWL is a bit different. So I'll just provide with a bit of a comparison there so to know how these translate between DL and OWL. And then we're actually going to look at what actually can you say using DLs. And then, okay, this can say, but then there's also constructors that you can use in these things that you can say that gives you greater expressivity. So we'll go through that, and from point 5 onwards, I will actually have an example ontology that we'll go through and create together. Okay, so the objectives of this is really to give you an intuitive understanding of the semantics of description logics. So I'm not trying to be necessarily 100% mathematically correct or tell you how to design ontologies. This is about semantics and trying to understand the meaning of description logics. I'm not going to cover everything in the constructions that you have available for DLs. It will only be a subset of that, mainly due to time constraints. And then if you want to follow along, maybe at a later stage, in Protege, what you need to make sure is that you have all these switched on, and that you, so all the inferences should be enabled, and make sure that you have this show inferences at the right side bottom of Protege selected. And then the reason that I will be using right through is Hermit. Then in terms of the forces driving DL research, the first one is expressivity of the logic you're using. And expressivity really says, or gives you an indication of how much you can say with an ontology, logic. So you could say either very little, or you could say a great deal. Then the other part that's important is computational complexity. Now, computational complexity have two axes. And the one is that it could be the time it takes can be very long. So your time complexity is quite high. Or you can have a high space complexity. That means your reasoning will end up taking a lot of space, or the algorithm takes a lot of space to run. Decidability is about a decision problem. So it's the ability to answer a decision problem. So a decision problem gives a question, and decidability gives an indication of whether this question can be answered. If the algorithm can answer this effectively, then and consistently, then that algorithm is said to be decidable for that decision problem. It's said to be undecidable if it sometimes can give you an answer, but sometimes it can't. And the problem then becomes that you actually don't know when it can give you an answer and when it can't give you an answer. So decidability is something that is of importance as well. Then if we now look at propositional logic, well, propositional logic is something that I think in any way is something that we end up using in our daily lives, maybe way more often than we think. So if I give you a sentence like A and B, this is the abstract logical sentence. You could have various interpretations for this sentence. So Zoe's dog, Zuko, if she tells you that he was barking, you may say, well, I think that was a true statement. But when James comes around and say, Margot, his cat was barking, you would think, maybe that was not a true statement. That's false. And you can have various interpretations. So There could literally be like an infinite amount of interpretations for these logical sentences. And you may ask, why are we dealing with interpretations? Why don't we actually just say what we mean? Why was this sentence A and B and not Zuko and Bach? I mean, why have these interpretations? And it's about, mathematics is about general solutions. So we try to provide a general solution, not just for a specific interpretation. You try to provide a solution for any interpretation. So you're seeking general solutions. And this sort of notion of interpretations is something you'll see in predicate logic, and there's something that you also see in description logic. So a sentence is called satisfiable if it returns true, if there's at least one interpretation for which it's true. So if we have a look here, this is an example sentence here on the right-hand side. So they say P and then in brackets, not Q or not P. Now, to determine whether it's satisfiable, what you can do is you can run a semantic tableau reasoning procedure over it. And what this procedure basically does is it will break this up in parts. It would say, well, for this to be satisfiable, I need P and not Q or not P to be satisfiable. Then it will break that further apart and say, well, for this to be satisfiable, we have to have either P and not P to be satisfiable, but because this, you can't have P and not P simultaneously. So this leads to a contradiction. So that is a branch of this algorithm that shows that that can't be done on that branch. But if we go through on this branch, we can have a situation where you have P that is true and not Q being true. And because that is a possibility, it means this is satisfiable. There is at least some interpretations for which this will be satisfiable. And if you have very large sentences, these semantic tableau trees can be very large. And in fact, when they do this, this is also the reasoning procedure that they use for predicate logic. And this is also what they use for some of the logics in description logics. And you can think if you run an ontology with 100,000 terms and I don't know how many axioms, that these trees for determining this reasoning or doing the reasoning procedure, they can become quite large. So for predicate logic and description logic, I won't go into it too much, but I wanted to show it here to just give you a sense of more or less what is happening in the reasoning procedure. But for the session, we will actually more focus just on the meaning of what the different description logic axioms and so forth mean. So then what is the advantage of predicate logic? Well, the advantage is that it has decidable algorithms for satisfiability checking. And these algorithms also have very good computational complexity results. The disadvantage is that they're not very expressive. So you can't really make general statements. You have to talk about specifics. So you have to talk about a specific dog called Zuko. You have to talk about a specific behavior, bark. So you can't talk of the set of dogs, for instance. And that is now where predicate logic comes in, because with predicate logic, you can now start making statements about sets of individuals. So if we have and the way predicate logic works is that you have your predicate and then it can have one or more parameters that it takes in. And based on that parameter, the parameters it takes in, it can return a true or false value based on some evaluation. So a very simple predicate is, as I've got it defined here for P. So if X is in the set R, it will return true. If X is not in the set R, it will return false. And potential interpretations for this could be, well, if we set S to be pets and R to be dogs, then the predicate will represent those pets that are dogs. But we could also have a completely different interpretation that applies to planets. And then we could have that the predicate P, for instance, represent the planets that are gas giants, for instance. Again, you can have satisfiability. So P is satisfiable if there's at least one interpretation for which P is true. And in that case, R will be not empty because P is true when X is an element of R. So R is not empty in that case. So example sentence is, for instance, for X and for Y, for all X and for all Y, PXY implies PYX. So you have this symmetric relationship between Y. And this is typical of interpretations like married to or sibling of or friend of. And I can imagine that you guys can think of many other examples potentially. The problem with predicate logic is that, or the value of it is that it's very expressive. But the problem is it doesn't have decidable algorithms for satisfiability checking. So this is where description logic then comes in, is that description logic is a subset of predicate logic for which there is decidable satisfiability algorithms. So the DLs vary with regards to the expressivity and the time complexity. So if you look at Shroik-D is the description logic that underlies L2, very expressive, but it has a reasonably high time complexity and space complexity. And the reasoner that you use there is Hermit. And EL++, on the other hand, is expressive, but not as expressive as Shroik. It has a much better time complexity and space complexity compared to Shroik. Then in terms of L versus DL, where L and DL sort of agrees is that they both call an instance or an individual the same, and that refers to a member of a set. When you L also then refers to classes. In description logic, you will refer to that as a concept. And these represent sets. A concept is a set of individuals. A class is a set of individuals. Object properties consists of pairs of individuals. That is, for instance, the married to set. Is there a question or something?
I was thinking whether it would be object property axioms that were applied to pairs of individuals rather than the object property itself. So you could have an object property on its own without it being applied. But
that's not completely true.
Okay, all right. So then I'm just giving my sort of owl-centric version of it. So I'm really interested to understand how that works.
Yeah, so if you look at objects and roles and the description logic definition, it's very much defined based on, so R is a subset of the domain of interpretation, a cross product with the domain of interpretation. So that's a very basic definition of a role in description logic. So if you look at data properties is where you have a individual linked to a data value, and you've got pairs of these, and that's your set. So that would be a data property, and that is referred to in description logic as a concrete role. Then your maximal domain of interpretation is L thing in this an L. In description logic, this is referred to as top, and it's represented by this sign that looks almost like a a capital T, but it isn't a capital T. So if you use LaTeX, that's the tool for representing mathematical symbols. It's represented by \top. And that represents the complete domain of interpretation, where then nothing and bottom represents the empty set. In L, it's nothing, and in description logics, it's bottom. That is the empty set, and for the empty set, they use this T that's fallen on its head in description logic. So again, not a T, and it's represented in LaTeX as \bot for the empty set. So what can you say in a DL or description logic? Well, the first thing you can do is like say, well, C is a subclass of D. And in description logic, what they would say is C is subsumed by D, or D subsumes C. And I've also provided you with a syntax in L for defining a subsumption. So the semantics of it is you have a set D, and then set C is subsumed by that set. So C is a subset of D. And the perfect example of this is, for instance, if you have the set of pets, then dog is a subset of the set of pets.
Why does it use the square subset of thing instead of the round one?
Because that's the semantics. So when they refer to the semantics, they actually use the round notation. Why exactly they use that notation, I can't say beyond that. So, there's actually some interesting parts in terms of the notation. So equivalence, so you could say a class E is equivalent to a class D. And with equivalence, you mean if you look at these two sets and you try to fit them on top of each other, they will match exactly. There's nothing sticking out anywhere. The way it's represented in description logic will be with this E and the parallel lines. This is equivalence. So, but that's also shorthand for E subsumed by D and D subsumed by E. Though if something is equivalent, it's best to state it's equivalent and not break it down into two separate statements.
I can have one interesting note here for anybody using obo-graph. Obo-graph, because of the nature of its reasoning, breaks this down. So you end up with these cycles with E subclass of D, D subclass of E. So just practically, you'll actually see that in obo-graph.
So also when you actually go into how a reasoner works, then actually knowing that this is the case is actually useful, or not useful, but it's something you need to know. Otherwise, you won't really understand how a reasoner works. So part of my training somewhere, we actually had to do this. Pretend to be a reasoner and do things stepwise like a reasoner would do, and then for equivalence you actually end up breaking it up in its parts. So semantics, as I say, the two sets are exactly the same, and I think an example of this is, I think we all would agree that if I talk of the set of humans and the set of persons, we will agree that these two sets are the same set. Okay, then you can have P subproperty of Q. So this is now where you have pairs of sets. So in this case, this is the Manchester syntax again the DL syntax. And here you have, again, that this is a subset of the larger set Q. But the difference between this and subclass is here, these are pairs, whereas with the classes, subclasses, we had single individuals. And the example of this is potentially, you would expect that the divorced from set will be a smaller set than the married to set. Mainly because you needs to be married before you can get divorced.
Then are they ordered pairs though? Like, is it?
No, yes, it is ordered. So usually, it depends. We'll get a bit into that, but usually there's the order is meaningful. So if I have a human owning a pet, that has an order. So something like married to doesn't necessarily have an order, but in some instances it does have an order, and that order makes a difference. Yes. So you have also, you can state that individual is an instance of a certain class. This is in description logic referred to as a concept assertion. So in Manchester syntax, you will say you've got individual C. Actually, I should have here class C as well. And then you say its type is C. There's two notations for concept assertion. This is C, and then the class C, and then in brackets the individual C, or you can have C colon and then the class C. As far as I know, this is the more recent notation. This is the older notation, though in an introduction to description logic, the book that Bradley referred to in the beginning of this session, they make use of this notation, the bottom notation. But that book has been started like in the 90s already. So even though it's only been published in 2017, it's been in the process of being written for many years. So in this session, I will make use of this notation. Then the semantics, you've got a class that's called C, and you have some individual that belongs to that class. And the example, a real world example of this would be something if we have the set of dogs, and Fido is a specific dog in this set of dogs. Then you also have role assertions. That is to say that one individual relates to another individual. And for that, you have defined some object property, and you have your individuals, and you define it as a P related to Y. This is the DL syntax again. Again, two different kinds of syntax. And again, I will prefer the top syntax there. And what this looks like in, if you try to represent this as a Venn diagram or something, you have X is related to Y, and this will be a set of many of these kind of relations. And example potential is like Carlo that owns Fido would be a real example. And this
might be helpful just to interject just quickly. If you're used to looking at functional syntax, it looks like the top bit of DL there, pretty much. So you have, it would be owns Carlo Fido for P, X, Y.
Yeah.
Yeah, just so that.
Well, so
we have to look at functional syntax when we look at diffs. So it's.
But okay. So what I've done now at this stage, and I just want to step back for 2 minutes. At the moment, what I've basically gone through is everything that you can say in a description logic. At this stage, there's nothing more you can say. So where's the complexity coming in? And the complexity comes in by the fact that when you say that C is a subclass of D, you can, what can be placed here in the place of C and in the place of D can be quite complex. That's where the description logic constructors comes in. So just instead of just having a concept, you can now actually have a whole description for a concept and that's where some of the expressivity of the description logic comes into a large extent. Some of this also comes from the roles, but for this session, I will be focusing on classes, not so much on the roles. Okay, so that's it.
How do you decide the distinction between something that's an individual and something that's a set, a class of individuals? It's like, for some cases it's clear cut, like there's that one instance
very
of dog.
Difficult. Can I ask that we talk about that at the end? And the only reason why I say that is So that can actually derail my presentation. Because there's very emotional debates about this. And I'll give you my opinion on that. And of course, I'm correct in this. I know I'm correct.
You touched on the trigger point.
So that's the only reason. It's not because I think it's a silly question or it's not an important question. I don't think we will get an answer in this session. Okay, so the one thing, there's two things that really trips people up when they come to ontologies for the first time in description logics in specific. And that is this whole open world assumption thing. And I think the first thing to notice is that why we struggle with this largely, I think, is because so much of our world, we think in terms of closed world. So if I was thinking of someone and I want to know whether they work at EBI, I would go and look in the SAP database. And if I don't find that person, I would assume they don't exist, or at least they're not an employee at EBI. That's not the approach that DLs take. And the approach that DLs take is they only derive something as being true in one of two instances. One, it's stated explicitly in the ontology, or two, it can be derived based on the axioms in the ontology from explicitly stated information. In no other way would it make derive information. So the absence of information is never a reason for an inference. And of that, I will show you one or two examples in this session. The other thing that is perhaps also not so obvious for DLs, for people coming to DLs for the first time, is that DLs do not make the unique name assumption. So if I go again to the SAP database and I notice that we have two individuals there, one Mary and one John, I will not for a moment think that these two individuals are the same individual. But in description logics, that could be the case. And you may have to actually say explicitly that these things are different for the description logic to assume that they're different. So this is just for number two. I don't have exact examples of this in this session, but I wanted to mention it so that you are aware of this when you come across it by accident. Now, what I want to do is actually start with a very small ontology that will be our little example, and I will do this with you as we go through. So we're going to assume that we want to create an ontology modeling humans and their pets. And for this example, we will assume that our universe only consists of pets that are cats or dogs. So I know parrots are beautiful, rabbits even more so, but for this world, we only care about cats and dogs as pets. Then we will also assume that we have a number of individuals, and Wolf will be a dog, Doggy will be a dog, Kitten will be a cat, Mary, John, and Sam will be humans. And I've very explicitly chosen the names to be not very, let's say, creative, mainly so that if we come across Wolf, we will know that it's a dog, and if we come across Mary, we will know it's a person. So just to make it simpler for us to remember what we're dealing with. So I'm now going to Protégé briefly. So I'm going to show you, I've got this open in Protégé already. So there's my human, there's my pets, there's my cat and my dog. So cat and dog is subclasses of pet. And then I have a number of individuals. Doggy is a dog, John is a human, Kitten is a cat, Mary, Sam, and Wolf. Okay, so that's my ontology at this stage. Okay, then we go on with the presentation. So the first constructor we'll look at is that of negation. So what negation means is if I have a class, it means everything outside of that class. So it's this class And if I say not this class, it's everything outside of it. So if I look at this example that we've got here, we have human in our ontology. And so remember, I said our universe, we really just deal with humans and pets at this stage. So we have humans, and the rest of our domain of interpretation is not human. And just notice that I keep on talking about the domain of interpretation, mainly because this is interpretation dependent. So if we decide our world to look different, then the interpretation will be different. So that's why I keep on talking about a domain of interpretation. So what we're now going to do is we're going to look at this in Protege. So what I want to do is I go to the DL query menu, tab, and here I will type human. Okay, and this is something that's given me a little heart attack earlier today. I need to start the reasoner. I keep on forgetting that. Start reasoner. And I don't want to chat to anyone.
Recording in progress.
Okay. So make sure that you have instances selected here on the right-hand side. So you see that you have human. I've selected you. My query is human, and it brings up as instances John, Mary, and Sam. And it should really not come as a surprise to us, because when we created our individuals, we basically said that John, Mary, and Sam are humans. So that's what's coming back. But now, if I go here and I say not human, and I say execute, I get nothing. So why is that?
Open world assumption.
Yes, who said that?
You're saying that.
Yeah, so it is open world assumption, and here's what's happening here. So we've said that wolf is a dog. We've said that kitten is a cat, and we said that doggy is a dog. Now we may know that a human and an individual can't be both a human and a pet at the same time. But in our ontology, as we have it at the moment, there's nothing that states that a human cannot be a pet, or a pet cannot be a human. So because that information doesn't exist in the ontology, it can't make that inference. So we can now go and add that inference, and the inference that we will add here is we'll add this disjointness statement. And what a disjointness statement is, so in Manchester, you have like this shorthand, so you can say pet is disjoint with human, but in DL, we don't have these shorthand. So you have to state it as pet is a subset of not human. And if we represent this graphically or with a Venn diagram, here we have human. So this is our complete domain. Part of this is human. The stuff outside of human is not human, and pet is a subset of that. So we're going to change our ontology to say that human is disjoint with pet. And we're also going to say, since you cannot have an individual that's both a dog and a cat, we're going to say cat is disjoint with dog. Okay, and I'm going to save. I've had problems with my Protege crashing, so I'm saving very religiously. Okay, so if I go now back to DL and I go and I need to go to the reasoner, synchronize my reasoner, and now you'll see that doggy, kitten, and wolf comes up again. Makes sense?
Mm-hmm. Yes.
Okay, just want to make sure that I'm not, my Zoom hasn't crashed by accident again. So thanks for the response. Okay, so that's disjointness. So, and yeah, I just show that that is indeed the case. We now get doggy, kitten, and wolf as things that are not human. So let's say we now want to model the notion of someone that's a pet owner. And let's say, I think we would agree that our definition of someone that's a pet owner is someone that at least owns one pet. And the way you can go and state that in the L or in description logic is using a quantified existential restriction. And the way you read this is there exists an R filler that belongs to C. Now, if you look to a pair, so remember, I've said that properties, object properties and roles represent pairs of individuals. So you have a first position and a second position. The first position in this definition is defined here, and you can see there it puts it in the first position. The second position is what they refer to as the filler, and this is this E here, and it says that the E must be of type C. So it says there exists an R filler, so this is in the second position, must be of type C. And if we try and understand the meaning of this is this is the set of individuals such that for each individual D, there exists at least one element E that is linked to an individual D of type C via the role R. So if we now represent this in Manchester syntax, so let's say we introduce a object property owns, and if we want to state that a pet owner is someone that owns a pet, we will express it as owns some pet. And we also will say, well, pet owner is a human, so we make it a subclass of a human. And pet owner, so if we go to the DL, we have an equivalent statement, and we say exist the owns role with a filler of type pet. And the pet owner is again a subclass assumed by human. If we try and represent this and as a Venn diagram, we again sit with human, our set of humans. Pet owner is a subset, and the individual here will have a link to at least one individual in the set pet. So there may be many individuals here. It may have many links. Each individual may have many links to pet, but at least each individual here will have one link to an individual that is a pet in the set of pets. I am going to update the ontology with this. So oh, I've already got owns some. I've already have an object property. Sorry, I'll show you. So there's my object property already. So there's an object property already that I've added previously. So pet owner, and I save this, or I'll do that just now. So, okay, now we have pet owner defined. And what we'll do now is we go and we will define some ownership for our individuals. So we're going to say that Mary owns doggy. We're going to say John owns kitten and wolf. So I'll do that as well. So we go here to individuals. Oh no, not there. And we say owns Wolf. I want to save this. And if we now go to the DL query again, and we say now pet owner, I just need to synchronize the reasoner. Then we have that John and Mary are pet owners, and that should not come as a surprise, because John owns Wolf and Kitten, and Mary owns Doggy, so they both own something. So that is actually what we would have expected. Okay, and there I also have a graphical representation of this again. So you have your set of humans, you have your pet owner. So John is a pet owner there. It has a link to Kitten. It has a link to Wolf. Mary has a link to Doggy. And Sam here at this stage, as far as we know, don't own anything, or at least not for our ontology's purposes. We are not aware of that. Just again, what this looks like in description logic. You will say owns Mary, Doggy, owns John, Kitten. And to James's question a bit earlier, that the direction here makes a difference. Though I think some dogs own their masters. Okay, so
it's commutative for cats.
Yeah, that's completely. So now let's say we want to model the situation where you have someone that has a strong preference for dogs, to the point that that's the only kind of dog, only kind of pet that they will have. So we want to model an individual that only owns pets. And the way you can do this is with a universal, qualified universal restriction. This is read as all R fillers are of type C. So that is read as for all R. This is our role or object property in this case, and this is of type C again. And again, you can provide this in Manchester syntax. So we have dog person owns only dog. And because a dog person is again a subclass of a human, we say it's a subclass of a human. And this is what it would look like in description logic. I'm going to add that to our little ontology. So I'm going to add a dog person as well.
How do you know they own only a dog with the open world assertion, though?
Please keep quiet until I've done my Good question, though. I'll address that in the next slide. But yeah, good point. Okay, so we have a dog person that only owns dogs. Okay, so now moving to the next part, and as we've said, now I'm going to look at dog persons. So we do this query. I'm just going to synchronize again. And if I now say dog person, actually correctly, as James pointed out, even though we've stated that Mary, even though we stated that Mary owns a dog and nothing else, I mean, we haven't provided information that she owns anything else. She doesn't come up as a dog person. The fact that John doesn't come up as a dog person is not a shock, because we know he owns a cat. But Mary, and James is quite on point, because we didn't make clear that Mary doesn't own anything else. And if we want her to make it explicit that she doesn't own anything else, we actually need to state that. And that is actually what I've suggested on the next slide. So we're going to say Mary doesn't own any. I just want to stop the reasoner for a moment. So Mary not owns So she owns nothing that's not a dog. And what I also want to do is I want to go further. I want to also say that Sam actually owns nothing. So remember, Sam is an individual that up to now we didn't say that they own either a dog or a cat. So we're going to add that.
You'll own nothing and be happy.
They have any clothes?
Okay, this is in this universe. This universe is about cats and dogs and
yeah, and I think when we build ontologies, we're ranging over the whole of reality, I guess. That's the idea.
Okay, so we start the reasoner again. And what we'll see now, if we go to DL and dog person, we'll see that Mary comes up as a dog person. But interestingly, Sam, who owns nothing, not a dog or cat or anything, also comes up as a dog person. And this is part of the semantics of universal restrictions that is a bit, for many people, it seems to be counterintuitive. But the way to think about it is that it doesn't have a counterexample to the fact that it doesn't own a dog. So this, it just don't own, Sam just doesn't own a dog. But or at this stage, what we saw in, if you look at the individuals, we didn't state that Sam owns anything, and in actual fact, we said they don't own anything, and they don't have an example where they have a owns link to something that's not a dog, and for that reason, they still fall into the dog person group. Now, that might mean that our definition is incorrect, but that could also be fine in some situations. That could be if you have, you could conceive of a person that's a dog person that used to have dogs all their life, but then develops an allergy and then can't have any dogs any longer. So they stop having dogs and they never will have dogs again. But if they could have a dog, they would have a dog. Yeah, that's a sort of way I think you have to think about the semantics of universal restrictions. In this example, what we will now do, because before we get there perhaps, so I've now looked at existential restrictions and universal restrictions. And I think at least when I was exposed to these myself initially, it was very difficult for me to understand how these things are different, because in some ways they sound similar in some ways, but also somehow different. So how are they similar and how are they different? So first, the differences. If you look at the existential restriction, an existential restriction, an individual that has an existential restriction to something else will always have at least one link via that relation to C. So if we have R from C, then an individual will have at least one link that is R link to individual in C. If you look at universal restriction, R only C, in that case, you may sit in a situation where that individual have 0 links via R to C. So that's the first difference. The second thing is that individuals may have links via R to individuals that are not of type C. That is based on the existential restriction. So existential restriction doesn't worry, or it's not, you could have a link to, so that individual will not necessarily, so if I have an individual that has an R link to C, but that individual also has an R link to, let's say, E, that individual will still be part of the set. Whereas if you have a universal restriction, if that individual has a link to something else that's not of type C, it will not be part of the set. Then in terms of things where they are similar, is that individuals may have multiple links via R to multiple individuals to of type C. So there's no limit on the amount of R links to C that they can have. That can be potentially even be infinite. And then the individuals may have 0 or more links via properties or roles other than R. So this restriction is about the object property R or the role R. It's not about other properties, object properties or role properties, roles. So if I have a property called P, this existential restriction doesn't say anything about that. This is only about R or object property R.
Well, I just wanted to ask, how can you be sure about the top left assertion in an open world model? Because what if the individuals aren't even aren't in our ontology?
That's possible, but open world assumption goes about what it knows about. So as long as you don't provide evidence to the contrary, that is fine. And you also have to state that there is nothing else. So as we've stated now with the Sam example, we've actually went and we did say that Sam doesn't have any other links.
But with the existential, you've stated there is at least one.
Yeah.
And then you've made a subclass. So then you've made an instance. So that's fulfilled by on the left. But when you make the universal, it can be, I always just think of it as 0. It can be sort of, you don't, if you say, I only have dogs as pets. Yeah. In this case, you might not actually have a dog as a pet.
Yes.
Perhaps if you did, you only would have a dog. But
so even if the explicit individual isn't there, you're saying that it exists. You're
with the existential, but you're not making that inference with the. So actually, you need to combine the two, which is actually I've skipped forward.
Yeah. So this is
towards your punchline. That's what.
You know, guys. Do you want to do the presentation? Please take over. I mean, go for it. No.
Please carry on.
So I think just maybe one thing is when the reasoner runs, what it also would do is once you assert the existence of one individual, from there it goes on and it starts asserting other individuals. And it basically, so even when you don't state the existence of individuals, the reasoner would know that some individuals would need to exist. And that's really part and parcel of the reasoning process, is the creation of these anonymous individuals, sort of. Yeah. Okay, so let's say we don't like our definition of a dog person that only owns dogs and then end up not having a dog. And the way we can go and address this is by saying that our dog person is actually a pet owner and it is owns only dogs. And then you use this conjunction. So if we go and do that, we go dog person. Sorry, I just want to stop the reason it confuses me. And I just add here on and as a pet owner. And if we recall correctly, we said a pet owner is someone that owns at least one pet. So if I now go back to here and sorry, I need to start. And if I do this again, you'll see only Mary comes up. Sam has disappeared. Okay. Okay, so the next example, what I'll do is I'm adding some additional individuals. So what I want to do is I want to add the individual that we call a pet. So we won't say, we just know it's a pet. We add an individual called Jill, which we'll say is a human. And then we will say that she only owns cats or dogs, or she doesn't own cats or dogs. And then we'll say she owns a pet. And what we want to do is, remember right in the beginning, I said our universe only deals with cats and dogs. So we might think that there's other animals in pets that, out there, but for this domain, for this ontology, we want to say we only have pets that are cats or dogs. So if I do this, then I would expect the inconsistency if my ontology is really capable of ensuring that I can only have cats or dogs. So let's see how it goes. So I'm going to add this individual. Okay, and we say Jill is a human. And we say then okay. So we have that. And we're going to say that she owns a pet. A pet. Okay. So at this point, I would expect if I run the reasoner, synchronized reasoner, I would expect that inconsistency. Instead, what I'm getting is it infers that Jill is a pet owner. And if I look at the explanation for this, it says Jill owns a pet. A pet is a type of pet, and pet owner is equivalent to own some pet. So instead of getting an inconsistency, I've got the explanation why Jill is a pet owner. So what's going on here? Okay, so let's have a look at what is happening here. So the way we've defined cat and dog at this stage, we said cat is a subclass of pet and dog is a subclass of pet. But with the way we've stated it, there's a possibility that there's this white space available around cat and dog, in which we could have individuals that belongs to pets that are not cats or dogs. So if we want to say that pet can be only cat or dog, then we have to ensure that that white space around it doesn't exist. You guys are still there?
Yes.
Okay. Just make sure I'm not talking to myself. It's entertaining, but so what we're going to do, sorry, I just want to show you here. So what we're going to do is we're going to add a disjunction. We're going to say that pet is equivalent to cat or dog. And I also provide you with the description logic syntax there. And this is what this will look like then if we try and represent this as a Venn diagram. So I would say pet is equivalent to okay. Okay, so if I run the reasoner now, I get an exception. I also, okay, then I get an exception.
Yeah.
Okay, I think my protege now has crashed. It's a very, yeah, okay, it's still sort of running. Okay, it's fine. So, and so if you get an inconsistency, what will happen is if you click on explanations, it can actually provide you with a list of explanations. So here it provides one explanation. You see there, one explanation one. And an explanation consists of justifications for this, why you saw this, why you have this inconsistency. So if we go through this, it says pet is equivalent to cat or dog. Jill is type not owns some cat or dog, and a pet is a pet, and Jill owns a pet. And this is why we end up with an inconsistency. So if you want to break an inconsistency, what you can do is you can go and ensure that one of these justifications no longer holds. So we can go and say pet, and we can go and remove this equivalence, or we could go and say Jill, well, maybe she just don't own cats, or just not dogs, and not both cats and dogs. Or we can also just say she doesn't own. So the main thing is, the moment you remove one of those justifications, your inconsistency will be removed. You will have addressed your inconsistent ontology. Now, in this case, we will just actually go and remove the fact that Jill owns a pet. And I think I need to stop my protege, sorry. I don't know, it keeps on randomly crashing. It's so annoying. And then what I'll do is I'll remove that Jill owns a pet, and then you'll see that our inconsistency has been removed. Jill, and we go and remove that and save. And we start the reasoner. And at this stage, all is happy, nothing. So we've removed our inconsistency. Okay, so that was disjunction. And that's just how this pans out. So the last thing that I just want to briefly touch on is domain and range restrictions. So for that, what I'll do is I'll just add two individuals, X and Y, and I'll say X owns Y. And that's all that I do for now. And we'll see what happens. We add Y. X. And we say owns, okay, sorry. Okay. And we save. And I'm going to synchronize the reasoner. Now, if I look at X and Y, really nothing happened here. So, and that is actually in a way expected. I just wanted to show you at this point, nothing happens. Okay, so now what we're going to do, and our next step is we're going to add domain and range restrictions. Now, again, domain and range restrictions are sort of these syntactical shorthands that exist in OWL that doesn't exist in description logics. So if I want to say for object property owns that the domain is human, the way I need to do this in DL is by specifying this axiom. And the range, to specify the range, this is specified by this axiom in description logic. So that shorthand feature doesn't exist within DL. It's really just normal axioms that you end up using. But let's do this now in our ontology and see how that changes things. So I'm going to say owns, and then I'm going to say the domain is human. And the range is pet. Okay, so and if I run the reasoner now, you'll see immediately that it will infer that the domain must actually be equivalent to pet owner. And if I click here for explanation of that inference, it would say pet owner is equivalent to own some pet. And because we said owns has the range of pet, it now infers that the domain actually is equivalent to pet owner, sorry. But also what you'll see is on X, it now infers that X is of type pet owner and Y is of type PET. And that is the semantics that's attached to domain and range restriction. Really, if you look at that, so you have individual X, you have individual Y, and the inference for domain restrictions only come into play when I say this individual is linked to that individual via this object property. Then it would say this is in that domain, that X needs to be of that type, and Y needs to be of that type. And I think I've got just the the screenshots again, but then that's it from me for this session. That was it. I hope that was useful.
Yeah.
Any questions? Besides the question James asked about deciding individuals versus classes.
We can come to that afterwards. I guess I've got one little comment on the modeling on the, so it was, I thought it was interesting that you chose to do pet owner equivalent to owns some pet, and then also make that separately subclass of human. So so that's a kind of pattern that we often try to avoid, or we use sparingly in the when we're building ontologies, because then you're saying that all you need to know whether, so then you can infer that if something is a pet owner, that is a human. So then that might be fine in the interpretation in this world, but that's kind of it's a bit of a strong statement.
I know Henriette has another blog post related to this.
Yeah, so it's the choice between making it pet owners. Yes, actually, that's like the previous slide. If you go, yeah, so you chose to make it equivalent to own some pet subclass of human, rather than equivalent to human and own some pet. I mean, it's fine, but there's those two sort of modeling options, and we tend towards the latter in a lot of what we build, because often what you don't want is a hidden classification coming up because you've asserted a, you know, so if I assert an existential restriction on something, an editor might not expect to get that extra classification. In this case, it might seem intuitive and fine. In other cases, it might be unexpected.
So what you say you would have done is you would have had it as equivalent to human and own some pet.
Yeah, that would be. I mean, occasionally we do use this pattern as well, but we tend to use it sparingly.
Yeah, look, I have to admit, I was way more focused on explaining semantics.
No, it's not a criticism. Yeah. It's actually, I just wanted to make clear to the, because yeah, I know it's a fantastic explanation of the semantics. It's really nice and clear. I really enjoyed it.
I think maybe Henriette, can you present in the next session about vector normalization? Because I know you have a pretty nice blog post about it.
Ah, that would be really nice, actually.
About what?
Vector normalization? Rector, or what? How you pronounce?
Yeah, as in Alan Rector normalization pattern. So it's actually Alan Rector's way of splitting up.
I remember that you had some blog post about it.
No,
am I wrong?
Chris Mongol.
Okay. Sorry about that.
Yeah,
okay.
No,
I could do a thing on rector normalization if you're interested, because it actually it's really kind of what we're doing with Uberon and CL, at least right now. So instead of taking a bunch of so you've got assertions in the cell ontology which are actually replicating information that's in Uberon. So in this case, there's a part hierarchy in Uberon, and then you partially replicate that in CL by making, you know, so I think in this example, you've got hierarchical parts of the lung. And then you have a classification which is based on where the cells are located, and that classification is replicating what's in Uberon. The rector normalization pattern is to try to have, as far as possible, two single inheritance classifications that you link and use one to derive the other.
Yeah. So that wasn't me, by the way.
Yeah, that's definitely a modeling rather than a straight
But
logic.
if there is something that you want to understand or so, ask me. What I've realized in setting this up is I actually haven't dealt with this in some time. It was actually nice to actually refresh my mind again how this works. On to James's question on whether you should use classes or individuals. And I actually would share my screen just for a moment again to clarify why I say what I'm saying. So people can become quite emotional about this, whether you should use classes or individuals. I would say when in doubt, use classes. And the reason why I say that,
but it's a seminar.
and the reason why I say that is because a lot of the semantics sits on the classes. So if you look here, there's actually on the individuals, there's not much expressivity that sits there. You can basically say something is of that type. You can say something is related to that, but beyond that, there's not much you can do with individuals directly. Whereas if you define it in terms of classes, you have a rich vocabulary to describe it. So, yeah.
So it's kind of like, why do individuals exist? Because, like, sorry, Deb.
I suppose there's a different. I mean, the way we would think about it in modeling for these kind of, we're sort of loosely building these realist ontologies, which are trying to model the way scientists think about the world. And I think that in that case, to me, the important distinction is, this is an individual jacket or an individual lanyard. So, an individual is something either, in this case, there is just one of them, individual hat, or you might have a bag of hats, and you could say that you could make that an individual and then have parts to that bag of hats. But that's a countable set versus what we're doing when we build bio-ontologies is things that range across all things in existence. So the range, when we have the term neuron, that ranges across all neurons that exist, or maybe that have existed, or that you can point to on a fixed slide or whatever. And then, in the so now when we come to model it in something like virtual flybrain, I have an image of an individual neuron. I can point to it, just one thing. Or maybe I have a single cell RNA-seq experiment and I've got 10,000 individual cells in a cluster. It makes sense to model that cluster as an individual, and then the individual cells, if we wanted to model those as parts of that cluster.
So one of the things that I usually would look at is also what is the inferences that you're interested in getting from the ontology. So, but sometimes even looking at that may at that point not be sufficient to help you to decide whether to use individuals or classes. Yeah, the only problem that I found with if people go with individuals is today you may be interested in this jacket and this jacket as an individual, but in time, depending on the situation you're dealing with, you may be interested in describing this jacket consisting of sleeves, consisting of various parts, and then you start having trouble potentially with that in, so you could have, if you have it in individuals and you have individual sleeves, you could say this is a related, and you can sort of provide that information on an individual level. But if you have sort of a generic description of it, it becomes difficult to make a generic description.
No, I mean, we've got like, what, 6 million classes in OLS and about 20,000 individuals. So
yeah, well, because we don't, I mean, I think in the sort of dream of lots of people building semantic resources with OWL, I think there was a big focus on you would have small ontology, or a vision that you'd have small ontologies and then very many individuals classified using them. I think it turns out in biology you need to be kind of careful using individuals, because we have quantified logic, all sum is kind of, biology is more fuzzy than all sum. So if I say, so we have, for example, a synapse to relationship that we used a lot to define classes in flies, and then classes of neurons, but that's fulfilled by the presence of a single synapse. And now we pull in thousands of individuals from connectomics data, and actually synapses turn up all over the place. Really what we're interested in is actually being able to say there's a functionally significant number of synapses in this part of the neuron, because biology is dirty. They just sort of, neurons promiscuously make synapses at a low level. So you need to be a little bit careful with how you use modeling with individuals. But we do actually use modeling with individuals in VFB and stuff. So it is, but then why would you put that on OLS? What you want to put on OLS are classes that people can apply to anything. So
so the individuals are there, but they're in the data, not the
They're in the data.
They typically end up in a RFD triple store for individuals.
Yeah.
The point that David does make, though, is I think with these sets that may not be always obvious when you think about it, is that in description logics, these sets are typically infinite. So yes, some of them can be finite, of course, but it allows for the possibility that these sets can be infinite. And when I talk about these links, those links can also be infinite, and they can have chains that go on forever and ever. And part of the reasoner challenges is to know when to stop, and that this is just going to go on forever. That's part of the complexity built into reasoners, is to understand when to stop this. Any other questions?
I have a question.
Yes, go for it.
You used ontology constructs to define the logic, but I am sometimes very lazy and tend to use rule-based logic to define those rules, such as if X is a person and X has pet, then X is a pet owner. Is there a difference between using all constructs and the rule?
Well, my immediate intuition would be that they're probably different, but what you will find is there's most likely some translation. So you also get L rules, the L rule profile. So you have to look at that. Off the cuff now, this is something I would need to look up to actually remind myself about that.
Actually, so there's a couple of things I could make there. We have used rules in the past, and rules. So you can write rules in OWL, swirl rules, but they apply across individuals. Yes. So then you can actually do really quite expressive things that you couldn't do at the class level.
Yeah.
And the other thing is, if you look at the reasoner work that Jim Balhoff's done, that actually translates into RL. And then does reasoning using RL reasoning. So Ubergraph is built on a lot of translation into RL and using RL reasoning. So that kind of fits with the second point, the point you were making.
So maybe just my understanding in terms of rules versus the reasoning you found in something like description logics and in propositional logic, there is actually a bit of a difference. So in L, they make inferences. In something like a rule engine or a rule language, that's conditions for actions. That's not really inferences. So the sort of inferences is because you have a trigger causing additional information to be populated into your RDF triple store. So the mechanism of these are very different.
But Hermit does support swirl rules.
Yeah,
so,
you can run both of them.
Yeah, and it's, I mean, you can do useful things like, actually, we didn't cover property chains here. That might be the one thing that would be good to add. But when you make property chains, you're just chaining together. I mean, if you think of it at the individual level, object, property, individual, and you make it. When you see a chain, you infer that another object property applies. But with rules, you can do things like partway along that chain, you can restrict to a particular class. So you can say, you can have a rule that says, if X is Y and Y is a subclass of Z, and and then keep chaining, then you can make. So that actually gives you some really powerful inferences that intuitively lots of people want in OWL, but you can only do it at the individual level. So that's actually being used by Go in their graphs of curating pathways and stuff.
But then that's individuals that's added to the ontology, or what?
It's you can make a rule which then makes inferences about the properties of individuals based on their classification, as well as chains of object properties. So there is, we do have, and then the big problem becomes managing rules, and nobody really quite knows how to manage these big libraries of rules, as far as I know.
It's similar to triggers in databases. Yeah.
Well, thank you, Henry. That was absolutely fantastic. I really enjoyed it, and I put off going to my next talk that's being recorded because I was enjoying it too much. So,